So here are Newton's first and second laws of motion, and as we'll see, they're actually really one and the same thing. So Newton's first law of motion says that if the forces acting on a particle are balanced, then its velocity will not change. So for example, if I just draw my particle here, a particle, by the way, is just a name we're using for an object, and we're modelling any object essentially just as one point mass here. So this is my particle, and I'm going to think about just the forces acting on it. So I might have a force acting on it in this direction of 25 newtons. Perhaps I've got a force over here of 20 newtons and another one of 5 newtons, maybe one up here of 3 newtons and another one down here of 3 newtons. All the forces I'm just drawing with arrows to show the directions. Then the 25 Newton force in this direction is going to balance out the 20 and the 5 Newton forces in this direction, and the 3 Newton force up balances out the 3 Newton force downwards. So we say all the forces there are balanced and the velocity won't change. But just note that actually this doesn't mean the particle's not moving. The particle could still be moving. So what the law actually says is that if the particle is at rest, i.e. if it's not moving to start off with, then the particle will stay at rest. It won't move unless there's some force that acts on it. But if it's already moving, then it will just continue to move with the same velocity. Okay, so it's actually, if there's no resultant force, there'll be no change in velocity. What Newton's second law says, the other part of this, is that if the forces on the particle are unbalanced, so they're not balanced, then the resultant force will cause the particle to accelerate. So for example, I might have a particle here that's got a force in this direction of 50 newtons and a force in this direction of 40 newtons. I could just redraw this just showing the resultant force, so that would have a resultant force of 10 newtons to the right here, so that's 50 minus 40, so 40 newtons of this force is sort of balanced by 40 newtons here, and then there's 10 newtons left as the resultant force. And actually that resultant force is a very important term to start using, is something I'm going to denote FR. And the reason I say FR for resultant force rather than just F is that we so often use F just as an individual letter representing a particular force. Like I could call this 50 Newton force F. So here, this is a really important concept, so I want to give it its own notation here. And the second law actually goes a bit further than that and says that if we have a resultant force that's not zero, an unbalanced force, then the acceleration that it causes is equal to Fr divided by m divided by the mass of the particle. So for example, if this particle had a mass of 5 kilograms, then the acceleration would be the resultant force 10 divided by the mass 5, which is 2 meters per second squared. And people often write this instead of A equals Fr over m. You often see this as Fr equals ma, or people often abbreviate it just to F equals ma. But as I say, I think it's much better to keep the Fr for the reasons I just described. As I said at the start, actually Newton's first and second laws are really one and the same thing, because if you think about the first law, well, in the first law, if the forces are balanced, then the resultant force Fr is 0, and what it says is the velocity won't change, so that means that the acceleration a is 0. So we've got Fr, which is 0, equals the acceleration, which is 0, times whatever the mass is. So actually Newton's first law can be seen just as a special case of the second law. But what we've got overall is this important idea that resultant forces cause accelerations, and they don't necessarily cause motion. It could be, that actually without any resultant force, the particle is still moving, but when there's a resultant force, it changes the velocity, it causes an acceleration. It's worth just saying something about the units here. So using all the standard units for this sort of problem, we've got newtons, kilograms, meters and seconds, and we've just got to make sure that those units are consistent across everything we're doing. So no reason we couldn't work in other units, although we do usually work in these units, but we must be consistent, so we couldn't have 10 Newton force and a 1 kilonewton force, I'd have to convert the 1 kilonewton force into 1,000 newtons before I started working with it, say. And we can see that 1 newton there, by the formula Fr equals ma, if you have 1 newton, that would be the force that's required to accelerate a particle of mass 1 kilogram at 1 meter per second squared. Okay, so here are a couple of examples of questions then, and in the first two we want to find the acceleration, and the last one we want to find f, so you might want to have a go at these before watching the solutions. So the first one here, we've got forces of 15 and 5 to the right and 35 to the left. So looking at the resultant force then, I could redraw this, so it's still got mass 3 kilograms here, but this is equivalent to just having one single force in this direction of 15 newtons. So 20 newtons here will be balanced out by 20 newtons over here, and leaving 15 newtons in this direction. And then the acceleration we've got then is given by the resultant force divided by the mass, which is 15 divided by 3, which is 5 meters per second squared. And that's an acceleration in the direction of the resultant force, which is to the left. So I'll put that in here with the double-headed arrow, an acceleration of 5 meters per second squared. In the second one, similar idea, so let's redraw it with the resultant force. So 500 minus 80 is 420 newtons in this direction. It's got a mass of 73 kilograms, so the acceleration is the resultant force divided by the mass, which is 420 divided by 73. I'm going to need a calculator to work this one out, so let's do that. 420 divided by 73, which gives us 5.75 meters per second squared to 2 decimal places. There's no exact rules on how exactly to round here, but I've got 2 decimal places here, 3 significant figures, usually good, it depends on the context of the question, but we definitely do want to round off here. The final answer we shouldn't leave as the full calculator to display, but if we thought we might use that answer again, then you could store the answer by going Shift Store and saving it to one of the lettered values. I've just chosen A here, and then if I need that again later I can just go alpha A and bring it back. So it's important to use the full value in any future calculations so we don't make rounding errors, but for the purpose of this sort of question we'll just round it off here for our final answer. And just notice the difference between these two answers as well. This one is actually 5.75 meters per second in to the right, and this one is going to the left. So there can be ambiguity if you don't make it really clear which direction it's going. Now here it's fine, I've just labelled it on the diagram showing what direction it is, but if you don't do that you do need to say something like left or right, or here I'd maybe say it's going in that direction. And actually if the question had been labelled here in the top one, say like this, and it had said find A, the answer would be that A is equal to minus 5 meters per second squared, because the acceleration is actually going in the opposite direction to the way that it's shown in the diagram. So there's no sense in which one direction has to be positive and the other has to be negative, but it's just relative to whichever way you label it. So if you label it that way, this one's going to be minus 5, and if you label it the other way it's going to be plus 5. In the last question we've got a slightly different situation. We want to find f, and this is one of those where, as I said, it's good that we reserve Fr for the resultant force so we don't get confused with this particular force, F here. So the resultant force, we've got 130, so they balance to give 70 to the right, and also an extra F to the right, so the resultant force is 70 plus F newtons in this direction, and the acceleration is 7 meters per second squared, and we've got a mass of 50 kilograms. So if we apply Fr equals ma, then resultant force is 70 plus F, that's equal to the mass of 50 times the acceleration of 7. So we've got 70 plus F equals 350, so F equals 280 newtons.